actually moving or not, we can check. Yeah, it's working. Perfect. Yeah. So let me formally introduce the next speaker of the plenary talk, Professor Urbasi Sinha. Urbasi Sinha is a professor currently at the Raman Research Institute, Bangalore, India. She is a known name in quantum computing and technology. She heads the Quantum Information and Computing Laboratory at RRI, as well as India's first project on satellite-based secure quantum communications. The lab specializes in experiments on photoning quantum information processing, including quantum computing and quantum communication, primarily using single and entangled photons. So here I invite Professor Sinha to deliver the talk entitled Some Quantum Experiments with Satellite Technology. Professor Sinha.
Thank you very much, Professor Raj, for this very kind introduction. And of course, thanks to Prashant and the rest of the QIQT organizing committee for thinking of me once again. Can you just confirm that you can hear me, see me, and see my slide?
Yes.
Okay,
yes.
Thank you. So it's of course a great pleasure to be back at QIQT. I have, been fortunate at, being able to talk in almost, I think, in all the QIQTs so far. And the first one was in 2019, I believe, and that was a physical event. And so it's a great, forum, and I really enjoy participating in the QIQT conferences. So this time I, wanted to speak to you about something which I did not talk in the last couple of years. So I just thought, to give you some flavor of the diverse range of experiments that we are doing at RRI. So I chose to talk about secure quantum communications this time, and specifically our project on quantum experiments using satellite technology. As was mentioned, I head the Quantum Information and Computing Group at RRI in Bangalore, India, and I also have affiliate faculty positions at IQC and CQIQC in Canada, and a Simons Eminoider Fellowship at the Perimeter Institute in Canada. So, well, this is a little bit of a light slide. So, we work with photons, and of course, I'm also, honored that this is in fact the first experimental talk of this conference, and it is, we are talking about photons in this. This year has been excellent for photons, with the Nobel Prize in Physics 2022 being given to entangled photons and experiments in quantum information, which of course has inspired a lot of the work we and my colleagues are working on globally. So it will be, unfair to say that photons, just because they are massless, they don't matter. So I found this very nice cartoon. Along with antimatter and dark matter, we have recently discovered the existence of doesn't matter, which appears to have no effect on the universe whatsoever. So I would just want to spend the next 45 minutes in, ensuring that you do not go away with the impression that in spite of being, massless, chargeless, and so on, photons actually, don't matter. Photons matter a lot. And in fact, secure quantum communications would not quite be where it is today if photons cease to matter. So with that, this is how our journey began. And this was in 2012. And in fact, one or two of the people here who came for the inauguration of the lab are indeed speakers in the conference, QIQT23. So I joined RRI March 2012, and this was December 2012 when we formally inaugurated the lab. So we have now, crossed 11 years of our existence, and it has been a fun ride. So a lot of what we do is motivated by this, very interesting quote, which of course the context is not what we are working on. Having said that, today's science is tomorrow's technology. And so at our lab at RRI, we tend to have a, balance between the fundamental science experiments and theory, as well as the technology experiments and theory. So we are trying to do hand in hand. So today I want to focus on some of the more, technology-oriented experiments that we are doing, but with a, very, very fine, fundamental science base, right? So without that, there is no security. So this is sort of what we do. And this is our lab website. And, with photons, we are working on these 4 different areas. One of them is quantum fundamentals, quantum information processing. Then we have quantum computing, quantum communications, and quantum imaging and quantum sensing. So these are the verticals that we are covering with photons. And today's talk is going to focus on the quantum communications aspect. Having said that, I know that QIQT has been primarily a student-centric conference, and so I hope that even through this talk you get to learn a little bit of what we do. And in fact, if you have more interest in this, I would refer to this one. And this is a very interesting article that I wrote, because this article was written right after QIQT 2019. And so I actually had given a tutorial on this for people who may remember from that time. And so this was published in Optics and Photonics News. It was an invited review. But then more recently, we have written a review in Progress in Optics, which I'm sure you're aware is a very important book that comes out every year from Rochester. And so the first chapter is ours on photon sources and their applications in quantum science and technology. So students, if you're interested, do get in touch with me. I mean, I'm not allowed to share this PDF online as of now, because it's of course a book, but then I can of course email to interested people personally. So with that, these are the current members of QIQT Lab, and and of course we've had many people who have been with us earlier and who are in different parts of the world, including India, doing some fantastic work in quantum information. Before moving on to quantum communications, just wanted to spend a couple of slides in giving you a bird's eye view on things that I will not really be talking about during today's talk. And so this is the bird's eye view of the lab as we speak, different experiments as they are in progress. The lab website is updated, at least the publications page and the lab members page, those things are updated pretty regularly. So in a nutshell, a lot of work we do is in quantum communications. The first one is the focus of today's talk, but we are also working on quantum relays and repeater technologies, integrated photonics-based quantum key distribution, as well as long-distance quantum teleportation and device-independent random number generation. So these are all various ongoing projects under various grant agencies from India. We have a very important thrust area on higher dimensional quantum computing and quantum information. And indeed, the idea is an effective interplay between fundamental science and novel technologies. And of course, with some, it's very nice to always see some acknowledgement, especially from the Department of Science and Technology in this case, as well as a lot of work, has been covered by various fora, including New Scientist and Nature India. So this is a snapshot of the experimental results from the lab over the last couple of years. I'm not going to talk about number one, which I actually talked about last year, which was the first loophole-free violation of the Leggett-Garg inequality that we performed and published in early 2022. This was a topic, I think, for the previous QIQT, which was, a quantum state estimation method that we found called quantum state interferography, which, sort of counters quantum state tomography. And then more recently, we have done this work on testing quantum foundations with quantum computers. Again, this is something I could have talked about today, but I decided that this will be what I'll talk about next year. So Prashant has to keep inviting me because I'm already telling you what I will do next year, because there is another work which is currently under review. So together I wanted to present this. So hopefully next year we have QIQT and hear about this. So today I'll talk about this work as well as follow-ups that we have done in secure quantum communications. So with that, quantum communication. So what is quantum communication? So quantum communication is a very vast area. And, one of the key areas which makes it, so if you want to talk about quantum key distribution based communication, because there are other ways in which you can do quantum communication, which are not QKD, right? But then if we focus on that particular topic, which we want to do for today's talk, the main quantum element there would be the key distribution problem. And it's probably right to say that this is quote unquote the most practical quantum technology, because a lot of, there is a lot of buzz, there is a lot of discussion about quantum computing, rightfully so. It's an excellent, technology, but it's not as practical, I would say, in terms of its availability in a kind of size and speed that is required for some of the real world problems. But quantum communications and quantum key distribution, on the other hand, is definitely at a higher technology readiness level than, for instance, the computing counterpart. So having said that, why you should worry about it? Of course, students specifically who may not be familiar with this topic, why you should worry about it? Well, we should worry about it given that, the 4 things that I have highlighted here. Somebody is annotating my slides. I would prefer if you didn't do that, Kuldeep Singh. I would prefer doing that myself. I needed to. Thank you. Okay, so these are the 4 applications, that I have highlighted here, which is, credit card purchase, online banking, electoral polling system. In day after tomorrow, we have elections in Karnataka, for instance, and defense strategic communication. So these are all areas which of course have a commonality. And the commonality is that these are all strategic communications. So you don't want your credit card details to reach the wrong recipient. You don't want your online banking to be leaked. Neither do you want your vote to go to someone else and so on. And for the defense sector, obviously, they don't want the very important defense secrets to go to the wrong recipient. So these are all linked together by being strategic forms of communication where only the intended sender and receiver should receive the information. And it is right to say that, all of this is at a risk of being compromised, for instance, by quantum computers. So currently the information is communicated through classical cryptography, okay? And so this will be compromised with quantum computers. So we need to take steps now so that we can prevent this obvious catastrophe, and the solution is quantum cryptography. So now what is wrong with classical cryptography? In other words, what is suboptimal about classical cryptography? The problem is that unconditional security is not possible. Okay. For instance, the RSA protocol, which is something which forms the basis for a lot of our public key crypto systems, is based on the mathematical complexity of factoring large numbers. Okay, which we know. So if I ask you what are the prime factors of 1, 1, 2, 3, 7, 1, it is a much harder problem than what is 3 times 7, which I'm sure many of you are already thinking is 21. So these are not, so these are one-way hard problems. And so a lot of our security is based on this one-way hardness of these problems. But here we have on the right Peter Shor, who actually came up with what is called the Shor's algorithm, which uses quantum gates that can perform factorization in polynomial time. In other words, it changes the hardness class of the factorization problem. And given enough number of gates and qubits, factorization problem stands to be compromised using, for instance, Shor's algorithm. Okay, so the point is computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. New algorithms can come for classical computers. We, of course, realization of quantum computers is already happening, and the ones which would break RSA are not far away. So my security or our security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. So this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And most important part here is the key distribution, which is what we replace by quantum means called quantum key distribution. So having said that, this is always something I like to show, that, the RSA protocol, when will it be broken and so on. So this was Krista Swore from Microsoft Research. She sort of said that the RSA 2048 challenge problem would take 1 billion years with a classical computer. A quantum computer could do it in 100 seconds. This was a bit of a statement, but we just want to qualify it by saying that a quantum computer which will employ Shor's algorithm to solve the factorization problem, for breaking this RSA 2048 challenge, it would require 4,000 qubits and 100 million gates. And it is fair to say that we are not there yet in terms of the number of qubits that we have in gate-based quantum computing. So it will take us a little more time to reach that level of quantum computer which would break this challenge. But then the way this quantum computing research is progressing, I don't know whether we have ever plotted a graph or something, but it's probably super exponential, the number of qubits that are getting added to the repository every year, right? So by the end of this year, IBM claims a 1,000 qubit machine, and soon we will have the 4,000 qubit from them or someone else. Maybe even our National Quantum Mission, which has been launched in India, will give rise to these large number of qubit quantum computers very soon. So we don't, of course, want to wait till this happens and it's a problem and it's compromised and then come up with a solution. We want to come up with the alternatives now, iron out the problems that these alternatives may have, so that we are ready and we have changed the paradigm by the time this sort of a computing facility, computing power actually comes through. So that is why it has to be done now rather than wait a few more years. Okay. So these are all claims. So how does quantum mechanics protect information? Now, of course, given that this is supposed to be a 45-minute talk, I will, of course, not have enough time to go through the details of all the arguments. But what I can do best is summarize the ideas of quantum mechanics, which help in doing QKD. So first of all, measurement disturbs the signal on an average, which we know. If the signals are non-orthogonal, then adversary cannot ascertain which one it is. And this is guaranteed by the uncertainty principle. Now, unknown quantum states cannot be cloned by an adversary, which is, of course, the no cloning theorem. And then, for instance, quantum correlations can be used to protect information. And this is example of a correlation is quantum entanglement. So these are the ideas or the principles or the methodologies in quantum mechanics, which primarily go into the key distribution problem to make it secure from a different perspective than mathematical hardness. Okay. So there are different approaches to QKD. We can have prepare and measure based approach, where the security is based on uncertainty principle. And the popular ones are the BB84 protocol, the B92 protocol. So these are actually a QKD community does not spend a lot of time in coming up with innovative names. They have a strategy. So these are the, the first letters of the surnames of the people who came up with this. So Bennett and Brassard in 1984. And so that makes it the BB84. Similarly, Bennett in 1992, and so on and so forth. So here M is Mermin and E is Arthur Eckert's E. Okay. And so these are the various common protocols, prepare and measure based, and then these are the entanglement based, where security is based on entanglement. Okay. So just for the students who are, of course, the primary audience, to give you a flavor for how we would do BB84 experimentally. So the general idea. So here we have, a single photon source. And the photon is then, so encoded in one of four possible choices of bases. So essentially, you have the rectilinear basis and the diagonal basis, and each of them has two basis vectors. So rectilinear basis, let's say HV, so it's called 0 and 1. And similarly, in the diagonal basis, you can have 45 and 135. These are polarization degrees, of course. And so again, this could be the 0 and 1. So you can have four possibilities. So this is my color encoding. So R0 is red, D0 yellow, R1 blue, and D1 green, and so on, just to make this more interactive as we go along. So these are the four possible encodings. Okay. So how does it work? So you have a single photon, it is generated. Then there is a very important ingredient called a random number generator. So the random number generator actually helps in this basic selection. So even the sender, traditionally called Alice, does not really know what she's sending in the beginning. So the encoding happens randomly. So she uses a random number generator, and the random number that is created dictates the encoding. So, so this random selection of bases happens. And so let's say it ends up being the red photon. That goes to the Bob module. Bob is our traditional receiver. For historic reasons, we call them Alice and Bob, and we will not change for this talk. Okay. And so Bob is receiving it. And so what does he do? He has to also measure in some measurement basis. And that selection is also random. So he's again using a random selection, and he's measuring something. So as you can see, we will have this series. So something is being sent, something is being received. And, because there is randomness involved at both ends, we do not know what is going to, happen. Alice and Bob don't really know where the basis has matched and where it hasn't. As you can see here in the bottom, I have just come up with some sort of an example set. And so what they do is, over the classical channel now, they share the information on their basis choice. They don't share the information on the results. They only share the basis choice. So only when the basis choice matches, of course, they will have the same bit on both ends, and for the rest of it, they won't. So the only thing that goes through the classical channel is the basis choice, and by knowing the basis choice on both ends, Alice and Bob know which are the bits where they have basis matching or basis reconciliation, and the rest of it they ignore. Okay, so this is what is called sifting. So in other words, prepare single photons using different methods, SPDC, the weak coherent pulse, and so on. Random selection of polarization basis, random selection between two orthogonal states in each basis, record timestamp and polarization state for each photon, send stream of photons to Bob. Okay, and then Bob's operation, the reverse operation, he randomly selects the polarization basis for each photon between rectilinear and diagonal, measures photon in each selected basis, record timestamp and polarization state. And together they send this timestamping and basis selection for each photon over classical channel, compare selected basis for correlated events, consider only those events where basis choices match, and discard the rest. Okay, so yeah. So these are basically the critical elements to be developed in QKD. Of course, the important part is the quantum source. It could be a single photon source. It could be a weak coherent pulse, and each has its, the weak coherent pulse has its cons and so on. So we'll discuss a little bit as we go to our own experiment. Of course, you need some robust simulations to actually have an idea of whether, what kind of key rates, error rates, symmetry, etc. you're going to get. Then, you have it for a particular protocol, which could be anything, but then we just discussed BB84. Then you have the sifting step where, essentially you just sift out the basis where they don't match, and then only retain the ones where it does. And for Indians, we would know, this is like, how we do this for atta, right? So you have all these little stones which remain on top of the sieve, and only the atta goes through, or the flour, wheat flour. And so that is what is sifting, really. It's not shifting, it's sifting. And then we have a series of classical processing steps, which we do, which are privacy amplification, error correction. And finally, we end up with the secure key, okay? So why do we then need entanglement for all this? We were doing this in BB84, we did not require entanglement. We require entanglement if we want to go towards what is called device-independent quantum key distribution, where we aim to generate a key between two parties in a probably secure way without making assumptions about the internal working of the quantum devices. I would like to request the chair to kindly ensure that students who want to disrupt this talk do not write on my screen. You have to somehow disable this or prevent them from attending, because it is a bit distracting to see yellow and brown lines on my screen. Prashant, are you there?
I think these are not by students. These are something, I don't know.
No, they may not be the students, but then, I see very senior people on my screen right now. I don't think they're doing this. So whoever is doing this should be prevented from doing this. And I mean, as an organizer, I would request you to kindly ensure this, because it's a little disturbing. But of course, I'm hoping that the ones who are listening to this seriously are not getting distracted. So with that, I will move on. So why do we need entanglement for QKD? As we have said, in these BB84 protocol, for instance, we saw that one of the elements which was necessary was the photon source, right? And so the photon source, you need to trust the photons. You need to, sort of ensure that the photons that are being generated from this source, they don't have any tampering happening at some level. Okay, and so there is an element of trust that we have to give our devices in the protocols that are prepare and measure based. But then we are, of course, in a scenario where we do not know how much we can trust our devices even if we have made everything from scratch, we are buying certain things. So we want to go towards what we call device independent QKD. And to do that, we require entanglement. Okay, so entanglement based QKD is the only known route towards device independent QKD. And longer distances are also possible through entanglement swapping based repeaters. Okay, so that is why we need entanglement. So having said that, this is an example of, entangled photon source that we have generated in the lab, where we have a concurrence of 0.995, and concurrence, for those who know, is actually a measure of entanglement. So highest value being 1. So it just says that, if you have a very high value of entanglement, that results in better key rates and lower error rates and so on. So we've systematically also studied this, and that is a detail. So, okay, so now we go on to the topic, which is, on quantum experiments using satellite technology, which is on long distance quantum communications. So why do we need satellites for QKD? So having said that, why do we need to increase the distance is the first question. So I can do a QKD experiment in the lab with my student, and very nice. We mimic Alice and Bob. We have a secure key. We can generate a message, but that's not the aim. QKD is a very practically motivated technology. So you want to use this in real life scenarios where, the stations are separated by longer distances. So if our Prime Minister wants to talk to the Australian Prime Minister, he or, they may not want to, they may not be using QKD themselves, but they'll get it done through someone else. But these distances are longer than what a lab scale demonstration will generate. So distance is important, and making it more practically viable so far as quantum communication is concerned. So ground-based experiments, they have some limitations. So for instance, if you want to do line of sight based QKD, so if beyond a certain point, the Earth being round or oblate becomes a problem, because you don't see each other beyond a certain point. The horizon is an issue. So typically you can go up to a few 100 kilometers, but not more. Then you would say, why not bring in a fiber solution? Fiber is a solution, of course, but fibers, the signals are attenuated in fibers, right? So optical loss is around 0.15 dB per kilometer, okay? And so beyond a certain point, you need to boost up the signal. And this is where no cloning comes in as a problem, because, you cannot just copy the signal and boost it up like you do in a classical repeater scenario. Optical amplifiers are not possible in that sense because of no cloning. So you need to have out-of-the-box solutions, and one of them is what is called a trusted repeater network. and this is something which is fine. So you have these, Alice to Bob, a few hundred, and then another node, and so on. But then a ground-based repeater network has an issue. It's a nice demonstration, but then it has an issue that, you're trusting all these nodes. And if indeed you want to use it for security, you have so many nodes that you have to really trust. If one of them is compromised, then the whole network is compromised. So this is not the best solution for actual security usage, but it's great proof of principle. Then there comes this, quantum repeater-based approach, where we have entanglement-based QKD, entanglement distribution-based approaches, which brings in quantum memories as well, and so on. So this quantum repeater-based approach is one of the most, R&D level, topics in long-distance quantum communications, because a lot of people are trying a lot of very innovative ideas here, but we don't really have a very long demonstration yet, and so a lot of excitement here. And then, of course, comes the satellite as a solution. Satellite you can use as a trusted node. So we'll come to that. So, and just to let you know that in India, we are also working on quantum relays, memories, and repeaters under the DST Quest program, which Prashant introduced in the beginning. And hopefully with the National Quantum Mission, we can take this to the next level and increase its scope and complexity. So this is something. And then, I'll skip the details of this one. So what about satellites? That's the main focus. So what happens is satellite bridges the large gap between ground-based quantum networks. So here you have a satellite. It is, spending some time on top of a ground station. And then, there are different ways in which it can be done. But then having said that, a satellite can travel a long distance in its, orbit, where it can access ground stations which are physically separated by thousands of kilometers. And that is what we are using in satellite-based QKD, by different approaches, which we will get to. Okay, and this is the general idea. So you can have a satellite which has an entangled photon source. I mean, I'm talking about entanglement-based QKD at the moment. So it has an entangled photon source. Then it can distribute one of the two photons to one of the ground stations, and the second one to the second ground station. And then by doing that, we can establish what is called downlink-based QKD. Okay, this has an obvious, this has been done by our colleagues in China through their MISSIUS satellite program. Okay, but then as you can see, this has a limitation in terms of simultaneous visibility of two ground stations. So depending on the height of the satellite, you can only simultaneously access a certain distance and not more than that because of a solid angle issue. But if we now do what is called uplink-based QKD, where the satellite is spending some time on one ground station, then it is in its orbit going over to a second one and spending some time. These two need not be simultaneously visible. That is a way in which you can actually have much longer distances possible. Okay. So, and this is, from NRC, they did this survey on what are the different distances possible by using different means. Okay, and so this is our big picture here. So we want to go towards this scenario where we have a satellite-based quantum communication between two distant ground stations, and then in turn the key here is distributed to all these different kinds of service providers, maybe through fiber networks, some through free space, and so essentially going towards what we would call the global quantum communication network. Okay, and so there are different approaches that different countries are following, and a lot of very interesting progress has happened from different countries all over the world. And so in RRI, we are working on different aspects of quantum communications. One of them is, as mentioned, quantum experiments using satellite technology, which is India's first project on satellite-based QKD. We are working on integrated photonics-based approaches as well with our colleagues in Italy. Then we have quantum teleportation, relays, and repeaters under the DST Quest program. And then finally, we have this project on device-independent random number generator and longer distance teleportation from our Ministry of Electronics and Information Technology. Okay, so quantum experiments with satellite technology, or QUEST, which is a collaboration between RRI and the Indian Space Research Organization. It started in 2017. Okay, and so what did we want to do? This was our MOU, and so the aim is to establish information theoretically secure quantum communication over large distances using a satellite. So perform quantum entanglement-based QKD between two Indian ground stations using an Indian satellite as a trusted node. This is the overall big picture, of course, and then take this forward and connect it with other satellites in other countries or, other ground stations. And one of those could be the project in Canada, which is being led by my friend and colleague, Thomas Yenewine, who is working on the KeySat project, which is again a similar project, but then based in Canada. Okay, so why is this experiment exceptional? Okay, so QuEST is India's first project on satellite-based quantum communications. And I would say, before going on to the scientific merits of why it is exceptional, I would say it is exceptional because, first of all, it started at a time when the field was not that popular. And, not everyone was willing to fund quantum technologies when I came back to India. And so, it led to a change in our mindset. And I would say that, some of its achievements have played an important role in putting India on the global map for quantum communications research. Security, of course, is our priority, and satellite-based quantum communications is necessary. But now we seem to think of it as a much more commonplace idea than when QuEST project, in fact, started. Okay, and so the Chinese satellite demonstrated downlink-based QKD. These are all fantastic papers which students should feel encouraged to read on what they have already achieved. QuEST aims at demonstrating uplink-based QKD. Okay, so it's never been shown before globally yet. The only other project is KeySat from Canada. Okay, at the moment, and so uplink allows for the photon source to be at the ground-based lab. Okay. And so this allows more flexibility with changing the source. So if, we launch the satellite with some photon source that we have created, if tomorrow a colleague from India or anywhere else comes up with a brighter source architecture, we can afford to replace that in the ground-based lab, provided certain conditions are met, much more easily than, let's say, if something has already flown. Something that has already flown, we cannot retrieve it to replace the source, for instance. So it gives us more flexibility. We can include quantum memory elements, after satellite launch. So it gives us a lot of scope for novel first-in-the-world science. Okay, and so why is it, however, having said that, it is also a lot more challenging than downlink-based QKD, for that matter, because there are many problems we need to resolve which are not already existing in literature. So in downlink, there is a vast literature now, thanks to Michius and some other efforts. But in uplink, there's very little literature, and so we are creating it as we go along. And there are problems and challenges that uplink has, which downlink doesn't. But still, we aim to do this when we even started, because of the tremendous benefits that we see, we will reap if we are able to solve the challenges. So it's a high risk, high reward problem which we are attempting at RRI. And so these are all various things which we have achieved, and I will in fact go through this anyway in detail, so I'll skip this one. So overall milestones, this was the first one that happened in 2020, which was an in-lab experimental demonstration of the B92 protocol. Okay, but then this was important for various reasons. First of all, it was India's first reported end-to-end free space QKD experiment, which was published in an internationally peer-reviewed journal. And it established globally competitive key rate and Q bar, so much better than the previous results, which were actually held by a group from NASA. Okay, and so this was the experimental setup. Then we went on to the first demonstration of QKD between two buildings using an atmospheric free space channel. This was February 2021 using entanglement. This was our setup. Okay. More recently, we have done again the first demonstration of QKD between a stationary source and a moving receiver platform. Okay, so this is very important, and we will talk about it in a few minutes' time as to why this step is very, very crucial towards our aim for satellite. While you can see that some of these demonstrations that we have done, of course, are global first, some of them are important to build capacity to do something locally sitting where we are. And so, demonstration of QKD between buildings using atmosphere or, of course, moving platform obviously have been done by other countries, including the satellite one. But then just because they have been done doesn't mean we can sidestep these steps, and straight away go to a satellite demo. It doesn't happen that way. We have to develop our own capacity, our own technology, and we are doing this in a systematic way with a lot of hard work from students and other colleagues. And this was the first such demonstration in March. And then another very interesting work that we have done, which has been accepted now and is going to appear soon, is on solving some of the problems that atmosphere brings in towards satellite-based QKD. And in the process, we have also turned software developers out of serendipity. It's not something we really intended, but it just so happened that it came out as a natural consequence of what we were doing. And this is also something we are taking forward very seriously. Okay, so this was, the B92, but then, given that we don't have a lot of time and I want some questions as well, so I will skip the details of the protocol here. You can always look up the paper later on or talk to me later. So the difference between B92 and BB84 is that in B92, you have two choices. Okay, BB84, you have 4, as we have seen. Here you have between 2. Okay, and so, and the QBA threshold is 4.8%. And so these are the various things you need: source, randomness, noise tolerance. And so measurements by an eavesdropper, introduces detectable errors because of Heisenberg's uncertainty principle. So these are the various components that we used in our Alice module for the experiment. Okay, and so we have used a heralded single photon source using SPDC. And so in fact, these are the kinds of attacks which we are able to circumvent from a possible eavesdropper by using this PNS type attack, photon number splitting, as well as attacks based on active random basis selection, because we have used a passive random number generator in our experiment. Okay, so this is the Bob module, and again, passive quantum randomness, no gated detection was required, and continuous record of timestamps, much motivated by the loophole-free Bell experiment that was done by the Zeilinger group as well. So similar ideas, but used in a QKD context. Okay, and so these are the snapshots of the experiment. Why B92? Somebody would say this was discovered 30 years ago. Why would you do this? I mean, in fact, that is what we do. These are the fundamental, I would say, protocols that exist, and the community is actually working on further and further refinements which aim to increase the key rate, lower the error rate, and increase the practicality of these protocols. And so a lot of changes are being brought about in the original scheme. But then, of course, we say it's a modification of the original scheme. So as I said, use of heralded single photon based SPDC, this actually compared to weak coherent pulse has an advantage in terms of security, in terms of the photon number splitting attack, which won't happen. Then use of true randomness or passive random number generator as opposed to active random numbers. Create correlating polarization with the temporal degree of freedom. Again, a detail, but this makes it tolerant to external noise. And then, of course, we have this very high key rate and QBA, which, to our knowledge, is the highest reported value achieved in a heralded single photon based P92 setup. Okay, and then, of course, we went on to do the encryption and decryption for fun, and as always. Okay, so having said that, another development that happened along with this experiment, which we established, is a software development, as I said. So we wanted to, when we started this off, several years ago, we wanted to simulate what kind of results we would get from our protocol by putting in the optical components, optomechanics, the detectors, everything, and to see what kind of key rate and QBA we would get so that we could fix our choice of experiment at that time. And so these were the various, toolkits that we found. These are all QKD simulators and so on and so forth. So, of course, with QKD becoming more commercially viable, advanced engineering techniques are being proposed. So, you can't just always test all of them in an optical setup. It's not very cost effective. We don't have that much funding. So simulator can accurately pre-evaluate the performance of these setups designs. And so that's what we wanted, and we found these available at that time. But what they were missing were these two important requirements. First of all, a quick and precise simulation of physical processes. Again, consideration of experimental non-idealities. That is very important. So see, when a person, whoever is doing software development usually tends to be a software developer. And so they may not be experimentalists. So experimentalists have an idea that, experiments are never perfect. So what are the various imperfect components in an experiment is something an experimentalist knows better. And so this sort of insight was missing in the available literature, which is what we filled by QkdSim, which we call QKD Experimenters Toolkit. Okay, and so we followed, these are all the various modules that we developed as a part of QKdSim. And essentially, this is the idea that we don't do direct testing. It helps in quick accommodation and testing of these techniques, considering physical process models, realistic imperfection, and experimental non-idealities. And we tested its performance with an in-lab implementation of the B92 protocol. So this is what is called the Agifol model of software development. So you can see it's a very modular structure. Various modules exist. So this is a waterfall model where you have one below the other in a hierarchical sense. But then each of these modules has an agility belt built into it, so that if tomorrow a student comes up with a better module, let's say for beam splitter, simulation, I can replace my beam splitter module with that. So there is a lot of scope for improving what we have started because of this AGIFOL structure that we have adopted. Okay. And so, I'll skip the details. It's an iterative approach, obviously. And then we went into a lot of very detailed algorithms for, statistics, figuring out the statistics required for the experiment using bootstrap methods, various optimization methods that we have done for the data analysis. And of course, the important thing, as you can see here, is, that the key rates and the Q bars that we have from experiment and simulation, they match very well, as opposed to what you would get when everything is ideal. Okay, and so this is our comparison of, we have done it at day, night, many types of comparisons. Okay, and then, some more details on how we have optimize these key rate and Q bars, which I will skip for now, but then it's important to note that if you don't do this optimization, if you have unoptimized window sizes, you can have arbitrarily high key rate and also Q bar. But we need information theoretic security, which we have been very, very careful about for all our experiments, that we want to do proper analysis of the security and ensure Q bar is below the information theoretic security threshold, which is what, these results, they exemplify the importance, utility, and performance analysis of our optimization strategies. These are the snapshots of various algorithms. I think there are 48 of them. And so this is what it was. So, the previous result using an SPDC based setup had a key rate of 31.6 kilobits per second and a quantum bit error rate of 10.5% over a 0.4 meter channel. And so our results, of course, had a much higher key rate. And this was not even information theoretically secure the previous one. So ours obviously is, and over a longer channel. So results match closely with the experiment. And as I said, single photon based SPDC security against PNS type attack, heralded photon noise reduction, 50-50 beam splitter for random selection, quantum randomness. And we are very pleased that, our work generated a lot of appreciation from, popular fora. This was, Nature India, IBM, QIQT blog, as well as, the Department of Science and Technology calling it one of its 20 major success stories, 2020. Okay, so now I go on to entanglement-based QKD protocol, and this is one of our most recent results where we have come up with a very new scheme for circumventing some obvious challenges that we would have to meet when we go through a lot of atmosphere. Okay, and so this is our polarization, entangled photon source, Alice and Bob setup, and so this was the protocol performance, so very high key rate. And here, the BBM92 protocol has an 11% threshold. So obviously we are below that and so on, and a very high key symmetry as well. And these are the source performance which we used for our experiment. So what is our technique? So long distance QKD implementation in which polarization of light is commonly used degree of freedom is becoming increasingly important. A significant challenge is that photon polarization gets affected due to birefringence in fiber-based implementations, for instance, right? Fiber scrambles polarization. Even in satellite movement in long-haul demonstrations, there is variation of reference frames due to the satellite movement in long-haul demonstrations. So conventionally, what people do is they use an active feedback-based mechanism, and this is employed for real-time polarization tracking. So as along with the QKD beam, they would have another strong beam, okay, which is used for active feedback. So many things have been done. In fact, Thomas's group has come up with a robotic arm-based technology, which is that all this is active. So you get active feedback on the kind of correction you need, and then you change the, at the source level, you play around and you get back the fidelity to being high again. Because of course, with the polarization scrambling, your fidelity with the entangled state drops, right? So what we do is we employ a polarization basis compensation method that obviates the need for active polarization tracking in satellite QKD implementations. And so our method's performance is independent of any local polarization rotation, okay? And so essentially what is the concept? So conventional methods, stochastic algorithm to dynamically compensate for any polarization fluctuations, robotized polarization correction based on an active control system, as I just said. So our approach without an active feedback, so essentially we perform a quantum state tomography at the output and obtain the reconstructed density matrix. Then we evaluate the optimal measurement basis choice that leads to a high anti-correlation in the outcomes. And we achieve the best trade-off between key rate, Q bar, and balanced key symmetry. So completely avoiding active feedback. This is our source and Alice and Bob setup. And so, for instance, this is the kind of state that we produce. Okay, so this is the result. This is the graph that I'm really very fond of. So as you can see, this unoptimized Q-bars, these are the blue dots. So these are measured in the conventional measurement basis. So we did an experiment where we, started off with a very high fidelity with an entangled photon. So, I mean, the 92, 94% fidelity we had. And then we systematically reduced the fidelity knowingly, okay? And so as you can see, it is actually going 80, 70, 60, even 10, which is not even the state anymore, right? So even with this, so as you will keep doing that, and this is of course what will happen when polarization is getting scrambled, your fidelity will change. So we went from a best case to a worst case scenario. And if you do not follow our method, then the quantum bit error rate also shoots up, right? So starting from something around 10, it goes up to some horrible number like 60-something%, right? So this is what would happen if you do the measurement in the conventional measurement basis. Now, the orange dots are what would happen if you measure in our optimized measurement basis. So which is what we're saying. So instead of changing the state and bringing it back to what it originally was, we let the state be, we actually play with the measurement basis angle. And so that is why we don't need active feedback. So we have changed it to an optimized basis. And so the unoptimized Q-bars, themselves, as you can see, they are pretty much a flat line. So irrespective of the fidelity with the entangled state, the Q-bar remains pretty much information theoretically secure, because this is because of LOCC, right? The amount of entanglement is what matters. It's not quite the form of the state, which is what we are using here, right? So unoptimized Q-bars measured in Pauli basis. Anyway, this is a detail. And these are all examples of various optimizations we have done to have further higher Q rate. And you can read about this. This is going to appear very shortly, and also a version is on the archive already. But then this is the important thing here, that the orange versus blue, how this would indiscriminately shoot up in conventional ones. And here you have pretty much a flat line. Okay, so usefulness, our method addresses important practical challenges in QKD demonstrations, correcting the polarization of light, which gets inevitably affected during long distance transmission. Active control systems having more parts than the raw system are more prone to faults over our method, which can lead to instability of the closed stabilization loop. Our method is cost effective, as the conventional active feedback system-based polarization are resource intensive, resulting in additional maintenance costs. And active controls obviously employ, trial and error methods to nullify the output deviations, which leads to an oscillatory response of the closed loop. This is not the case for our method. So in summary, our method serves as an effective tool towards enabling efficient long-distance quantum key distribution implementation for both fiber-based and free space approaches. Okay. So this was one of our recent results, where we are trying to solve certain problems by using quantum mechanics and quantum information. So I will take 5 more minutes because I started 5 minutes late, if the chair permits.
Yeah, yes, no problem.
Yeah, okay. So, I wanted to show, because students are, of course, still online, so I wanted to show a little video of our free space quantum communications through an atmospheric channel. And, so this is what we do. We take the photons from the lab, we project them outside using, refractive optics here. So this is our ALICE module, as you can see, not, with a little bit of detail. And so it's coming out of the lab, okay. And then, of course, the photons are going across towards our Bob lab, which is, a separate lab across campus. And so this is our distance. And so inside they go into yet another, a Bob module, a Bob measurement station, which has optics and optomechanics, which you saw the schematic of, but this is just to give you a feel for how things look inside the lab. I thought I'll show you this video. So this was, of course, the first demonstration was in February 2021. Okay, and so we again had a lot of appreciation for this work, including in the vernacular, which we are very pleased about. Okay, but then this distance, this demonstration we did was across a 50-meter distance. Okay, and the 50-meter distance was chosen because for people who have been to Raman Research Institute, you would know that I think we have more trees than human beings on campus. And we are, of course, very possessive of our trees. So we have very little line of sight where there is not a tree which comes into our, line of sight. So this 50 meters is the only, distance we could manage where there is no tree in between, which we had to cut because we don't cut trees. However, there was a lot of discussion later on about some follow-up experiments which happened from 1 or 2 other groups where they did 200 or 300 meter. And a lot of hue and cry really about this distance. So we went on to, of course, doing a more detailed analysis of whether really we were lacking anything in that 50 demonstration. Of course, the answer is no. Here we have done, simulations involving all, different kinds of atmospheric conditions. For instance, humidity and temperature. And as you can see, 200 meter, we have this kind of loss. 300 meter, we expect this kind. And even if you go to 500, which hasn't been done, we have this kind. So what will it mean if if our experiment had these kinds of losses? And so this is what we went on to show next. So experimentally, we put filters to induce attenuation in the photons, and the resulting timestamps will generate diminished key rates proportional to the attenuation. And so as you can see, this is what we found in 50 meter distance, but even up to 300, it just goes from 10.2 kilobits per second to something like 9.5. So it's not really a very big drop, and we don't expect a very big drop over a few hundred meters. The big drop will happen when you go to kilometers or even, more. And so it was quite natural for us to choose the distance, which was, because of our geographical location, but we went on to actually do some detailed analysis to show that, in fact, this was as good a demonstration or better than any other which followed. And more recently, what we have done is, we have actually taken the complexity to the next level. So, our aim is to do satellite-based quantum communication. So the satellite is not going to remain stationary on top of me and we are going to do communication, and that's not going to be how it is. The satellite is going to move. So we need to keep tracking the motion of the satellite. We need to keep pointing towards it and acquiring quantum bits, data for quantum communication. So this pointing, acquisition, and tracking system is very, very complicated for entanglement-based QKD, especially when you do uplink-based QKD, because you hit the atmosphere immediately. So you have all the problems of the atmosphere hit the photon as soon as it comes out of the source. So naturally, there is a lot of precision required in the kind of patch system we would need. So we have been systematically developing such systems in the lab. So these are all the linear ones. And in fact, and so we have been showing through different iterations of patch systems how we are able to, correct for this motion of the receiver by using, the detectors and the image, the camera and so on and so forth. So this is something. So I don't know, it has a bit of a sound, but then having said that, just to give you an example of how it works in the lab. But I'll move on to this one, which actually was something which was suggested to us by our space agency, that, we've done this very nice experiment where we have been able to correct for the motion, but what about making the motion circular? So we actually created this circular track here at RRI. This thing was built in home built, and then, the correction is happening now for the system, which is now moving along a circular track, which is what a satellite is expected to do. And so this was, the next iteration that we did, where we were able to do this for the circular track, which pleased our funding agencies very much. And then finally, in March 2023, we did this, entire, we created an entire vehicle, okay? And so this has the complete Bob module, along with the patch mechanism, as well as synchronization, and everything is, this is almost like, a larger version of what we could miniaturize, optimize, and fly in an eventual satellite. So this is what we call the moving receiver platform, which again was completely home built. And so we have been able to show quantum communication between a stationary source and a moving receiver platform in March 2023. Okay, and so this is a little group of people who actually did this. And again, it's the first demonstration from our country, and received quite a lot of appreciation again for our efforts. So, and with that, I finish my talk hopefully on time. So thank you very much. Over to the chair.
Yeah, thank you very much, Professor Sinha. So I take the liberty to ask one question.
Okay.
So as you are doing experiment, so you have the liberty to reframe my question that who are your competitor inside our country? Or you have the monopoly in this business from the experimental point of view, I would say.
That's a fun question to answer in a recorded talk. Yeah. I mean, so what I would definitely say is, our work and our sincere efforts have led to, one or two more groups who have started working on similar ideas, and they have also been doing some very interesting experiments over the last few years. But then in terms of, I would say that with the launch of the National Quantum Mission, I'm not looking at competing, but I'm looking at a cooperative effort. towards actually demonstrating this over different ground stations with different groups pitching in with their ideas, so that we have a quantum communication network within India to begin with, and then take this to other countries. So this will succeed if we leave the spirit of competition and come in a collaborative framework. And for that, we need to respect each other's achievements and acknowledge them in public fora. I hope that answers it without naming people. Yeah, thank you. I think I see certain things come up in the chat. I don't know whether they're okay. I have one question. Can we use radio frequency for this? Can I answer that? Yeah. That's actually a very good question. So I mean, RRI is an organization which not only does very good quantum technologies, but also radio astronomy. And so in fact, one of these things has been a constant discussion with. So see, radio frequency has an advantage that, it's long wavelength, right? So this thing that I'd spent the last few minutes telling you about, the precision level that is required for us to be able to keep pointing and, acquiring, that precision level will be lower for longer wavelengths. But then the problem is we don't really have, at the moment, entangled photons at that frequency. So we are actually limited to the kind of, wavelengths which we are able to naturally create in terms of entangled photons. We are doing entanglement-based QKD. And so we don't really have that solution, but that would be a great next step to, reduce the complexity and maybe, maybe even have brighter sources and so on. So it's definitely not something I would disregard, but at the moment we are sticking to windows in the atmosphere where we have good throughput, good pass, as we call it, for certain wavelengths, and sticking to wavelengths which we know how to create entanglement with, you see. So yeah. And the second question here is it possible to leverage the outcomes of an experiment or a similar experiment utilizing quantum entanglement towards the development of the next generation of quantum radars? If so, could you provide a brief overview of the potential implications and possibilities? Yes, quantum radar is a very interesting topic. And I mean, it is actually, unfortunately, the topic is very interesting, but then a little bit of miscommunication is there in it. I mean, as to what is possible, what is not. But then, of course, by using quantum entanglement, we will be able to, get some of these ideas, and some of it is already happening. There are experiments globally where people are looking at this topic. But in my personal opinion, I think, we are not as mature in that, let's say, than QKD. So, we can use entanglement, we can use the correlation to, of course, image things, that is being the general idea. So if I hit something, some object, and, it comes back to me, so then I will know of the presence of that object because the photon which hits it and comes back is correlated with the photon that is perhaps in my lab and so on. So these are ideas that are gaining a lot of traction. Of course, answer to your question is a simple yes, it is possible, but then exactly how feasible, how practical, I mean, of course, is a detail. Then there is a question on there exists QKD techniques without entanglement. Is there any advantage? Yeah, of course. There exist QKD techniques without entanglement. I spent a lot of my talk telling you about an experiment, which was a modified B92 protocol, which did not use entanglement. And as I said towards the middle of my talk, entanglement-based QKD gives us the option of going towards what is called device-independent quantum key distribution. And so that is something which, we are pushing towards as a community. And if we want to do that, then of course we need to do entanglement-based QKD, and that is the advantage. Secondly, entanglement, has a natural inherent randomness. So entangled photons have a inherent randomness ingrained in them. You don't need a random number generator on top for like we are doing for the prepare and measure based QKD. So that randomness comes in handy and is utilized in many entanglement based protocols. Next question is, what if we explore the utilization of geostationary satellites for entanglement-based QKD? In doing so, could we potentially enhance the precision and efficiency of such systems? That's a great question. And of course, geo is going to be, so we are currently focusing on LEO because, we want to, it's a bottom-up approach. We want to show, and of course, these are not things which you and I mean, I don't know who Samir is, but I'm sure he's not richer than me or poorer than me. I mean, as academics, if we are all academics, I don't think we can afford to do satellite-based QKD just sitting by ourselves and fiddling with it in our lab. These are huge resource-intensive problems. So we want to go in a bottom-up approach where we show success chronologically, right? So if we can do this with LEO and we show that, this thing in principle works, obviously, if we go to GEO, naturally, we will be covering a lot more ground there, literally and otherwise. But then, it's also 36,000 kilometers. So, I mean, so we will go LEO, MEO is Middle Earth. And so Leo, Mio, Geo, that is how we would progress, of course, as a community. But we don't want to start with something even harder than what it already is, in my opinion. So we would do Leo first. Hopefully it works, because already so many unknown problems there for uplink, which we don't know the answers to. Some we do, some we don't. Yeah. So I think that was the last tight question, Professor. Okay. What wavelength do you consider optimal for the satellite communication? What do you think of E91 compared to, well, I suppose BBM92 is what you have in mind. So the wavelength that we are currently considering is near infrared, so hovering around 800 nanometer, which is actually a very nice window. So we have done a lot of analysis for the atmosphere and so on. So that is a very nice window which we are aiming for. And regarding E91 versus BBM92, well, of course, they're both entanglement-based protocols. But as we know, E91 uses the Bell inequality violation as some sort of a witness during the protocol itself, whereas in BBM92 we are not really doing any such what should I say, in situ measurements compared to the E91. So I mean, I would say they are both very nice entanglement-based protocols, but we have a preference for BBM92, which I can discuss offline, because that information is not, I have a non-disclosure agreement on this particular project, so I can tell you about things which are in public domain, and our preference for BBM92 is not yet reported. So Professor Raj.
Thank you very much to all audience, and I think there is no more any post. And I would like to thank Professor Sinha for giving a nice experimental talk. And now I return, Digambar.
Good afternoon, ma'am. This is Digambar Padulkar,
Yes.
Research scholar from COIB Technological University, Pune.
Okay.
Ma'am, currently I'm working in quantum cryptography, and I'm using secret sharing for medical data to be shared among the different parties. But right now I am finding difficulties to conduct the experimental work. So can we focus on the experimental facilities associated with what the topic of mine in RRI?
Of course, that is a discussion which we should have not as a part of this conference Q&A. But then, yes, at the moment with the launch of the national mission, we, of course, are very interested in ensuring that all the relevant stakeholders in different parts of the country, we can come together so that we can help each other achieve what we are missing individually, so that we can work together as a collective instead of individuals. And this falls very much in that purview. So kindly get in touch with me separately, though, because, this is of course, ultimately a conference.
Yes, surely.
Thank you.
Thank you, ma'am.
Thank you, everybody. I'm returning back to the organizer for if there is any announcement. Okay.